Euler's method for numerical integration. Euler's method is a numerical technique used to approximate solutions to first-order differential equations of the form dy dx is equal to f of xy. What we mean by that is it might be something like dy dx is equal to xy take 1 over y minus x, or something like that. So it's the dy dx equals and then some function that contains x and or y on the other side. It works by taking small steps along the tangent to the solution curve. We'll have a look at a diagram shortly, using the slope given by the differential equation. The steps of Euler's method are as follows. We start at the initial point, x0, y0. So there's some point here, x0 and y0, where we want to have a first step in trying to predict values along the solution curve. We then calculate the slope f dashed at x0, y0 at the current point. So that slope might go like this. I've probably drawn that a bit too far up. We can see the curve there. So it would be the actual tangent of the curve. That's probably not too bad. We use this slope to predict the next point. x1 is x0 plus h, and y1 is y0 plus h times f dashed of x0, y0, where h is the step size. So in other words, what we're going to do, we're going to go along the tangent like so to our next point. If the step size is h, that means x0 plus h would be the next x coordinate, and then what we do is we calculate h times f dashed of x0, y0, add it to y0 to get the next point, which is y1. So y0 plus h f dashed x0, y0, and what we do is we use this point now as our x1 and y1, and we repeat the process. So we would then take the gradient at this coordinate, it would be at the coordinate where we are, and we would go off in this direction and so on, and we'd repeat the process. So repeat the process to extend the solution over the desired interval. In general, xn plus 1, the next x, is the current x plus h, and the next value of y is the current value of y plus h times the gradient at xn, yn. Alternatively, we can write this as delta y1, that's the change in y, is dy dx evaluated at x0, y0 times h, and then, as before, x1 is x0 plus h, h being the step length that we go in the x direction, and y1 is y0 plus delta y1. In general, delta yn plus 1 is dy dx evaluated at xn, yn times h. So that just means the next change in y is the gradient at the current point times the step, and then the next x is the current x plus h, and the next y is the current y plus the change. This diagram's a bit better than the one I just drew. So what happens is we start at x0, y0, and then h is the step length in this direction, we, using this tangent, compute delta y1. That moves us to the next point. And then we recompute the gradient there, and we'll head off along this way, going h along in the x direction, compute the delta y2, and that gives us our next point. And then we would just continue like that across the desired interval. Many differential equations in reality are actually solved like this because some differential equations are actually insoluble algebraically. In order to get an accurate result, you need h to be small. Now, it won't be in the examples that we do manually, but a small value of h, especially where you have a steep gradient, if the gradient goes down very steeply like this, and you're computing the gradient up here, and so you go off in this direction, you end up a long way from the real curve. So small values of h are needed to span with reasonable accuracy. We'll have a look at that as we go through the following examples.